Sure. Thanks for the introduction. And as discussed, I mean, feel free to ask me questions. So I'm very excited to be here to talk about our recent works on giving formal guarantees on frontier AI, which involves like large language models. This is joint work with a lot of collaborators, and some of the work I will be talking about has actually found place in adoption in industry. For example, Amazon is using it in talks with like General Motors to have some of these research also used in their product. Also, NSF, they have Nair, Isha, I think she's in the attendees, is trying to port these things into the models that NSF Nair's project is also hosting, right? So I don't have to waste time by saying how impressive AI are and what are the problems, but these are just some anecdotes I have put together. One is like the insurance companies don't want to cover AI because no matter the hype, they know that it's risky. And the bottom one is like a survey from Stack Overflow around like 30,000 respondents where they are asked about what are they concerned about agents. And it's not about necessarily the adoption or the lack of skills, but they're concerned about the security and privacy risk. So the point being that these models or agents are good for isolated one-off projects, but at the enterprise level, when you're going to handle large amount of data and files and so on, people still don't trust these models. Uh, yeah, I mean, this is something we have also been looking beyond in terms of computer science, that's just the AI safety research, but more like into the economic impact of these models. So in the economic literature, and that's something I'm doing with other collaborators, there is this talk about the jaggedness of AI capabilities, which means that for two similar tasks that have the same uh, difficulty level for humans, for some tasks the AI can outperform humans, but for another task it just is very bad. So this is what is being shown here on the left hand side. Blue, if you look at the boundary of this blue circle, it's a conceptual illustration. It's all the tasks that humans can do at the same difficulty level. And the red one, which is the discourse currently in the economic literature, you might have heard of some mass hysteria events like these many jobs are going and blah blah blah. That assume that what AI can do, right? So if you look at what AI can do, you get the red shape, which is jagged currently, uh, but it's an optimistic view of what AI can do. And what we believe that this view is too over optimistic because it does not take into account the risks involved. And once you include the risks, it becomes more jagged and less tasks that it can do reliably, right? So the goal is not to like say AI can't do anything, but to think about uh, what task or what kind of things that AI is good at while eliminating risk, and how can we use some of the research we are doing to like make this frontier even better. So one of the things we are hypothesizing is that as the model's capability increases, the red thing, which is just capability based jaggedness, will smooth out and AI will be capable of doing a lot of things, but the risks will remain, especially the adversarial risks. You might have already seen that discussion about anthropic mythos, right, where they are saying they don't want to release it because it can cause some cybersecurity risks. So you can imagine for many kind of tasks, even if the model is capable of doing things, this risk will remain. And one way to get rid of this jaggedness is to have some kind of formal guarantees, and that would be the on how much you can rely on this, right? So that would be the focus of this talk. And then here, I'm not here to talk about, oh, formal methods can give the most uh, strongest guarantees possible. And if you read the papers, and I was talking before with Orpheus, is you read the paper and then you don't want to use formal methods because they just make it seem like formal methods are hard. So my goal is not to like impress you. My goal is to inspire you, to tell you that formal methods can be applied for these models. And then I'm not here to talk about the strongest guarantees, but some guarantees that defines progress. It's better than what people have been doing. And then we can have more people doing these things, and then that builds a bigger community. The point being, we have to start somewhere. So how are formal methods useful for LLMs? You can use it for offline evaluation. This goes into the territory of, uh, like evaluation, but you are giving formal guarantees. So a lot of literature exists in formal, and I think in this seminar series, I think there have been other speakers who have talked about formal guarantees on models before you deploy them. And the second thing, which if I will have time, I'll try to cover, is how you can give, like how you can do online monitoring and enforcement. So once you have decided your model is good enough, how can you use formal guarantees to improve safety as well as utility? And you can also use these things for training and interpretability, something we have done, but will not have time to cover those. So I'll focus on the offline evaluation where the goal is that you are given a model and you want to assess how good it is. So again, the goal here is not to give the strongest guarantees, but use these guarantees to build some metrics to be able to compare models. So we have been working and been very active in this space. So I have been working on neural network verification for 8 years. So we have designed some of the popular systems based on abstract interpretation. So for AI models, what are the two main components? You need a formal specification which describes the expected safe behavior on some large set of inputs. And verification algorithm which checks whether the model satisfies the specification. So the number of specification traditionally has been used as a metric to compare different models. So if you have two neural networks that get the same accuracy, you can use the number of specifications satisfied to compare them. And that's something we have also put into practice when I was like doing postdoc at VMware. We use this kind of verification methods for the developers to get more insights into their models. And traditionally, the kind of things people have been verifying and still verify is like the robustness specification, where you would have, let's say, a correctly classified image. You would consider some L infinity ball around it, and you would like to prove whether all the images are classified correctly, right? And abstract interpretation is a very popular framework. It's also like there are many people doing these things, so they also call it bound propagation, where what you will do is you would do an over approximation of the layer outputs. So we even have like a monograph which on this topic, which covers all the different things in greater details. We are still active in this area, but more in the probabilistic settings, right? So the problem has been that how can you do these guarantees for large language models? So I consider that there are a few challenges and obvious ones. Um, Informal specification. So they handle a large and diverse set of prompts that you cannot capture by just doing some norm-based perturbation around tokens, right? Because there's also like semantic changes in the way users use these LLMs. And then the robustness was usually like, oh, I have some linear constraints over the output of the model. You can't really specify if a output is harmful or not harmful with the use of a linear constraint, right? And how I see large language models is a neurosymbolic system that combine high dimensional continuous computations with discrete algorithm dependent decoding steps. And also like the embedding layer is discrete, the conversion from tokens to like embedding. And then the important thing I want to point out here, and that's kind of overlooked in all this literature, you would hear that people complain about, oh, my LLM is stochastic and I can't get a uh, uh, I think there's some question and I will get to it soon. But in general, I think there's that discussion about randomized smoothing. I personally, despite the hype, don't, I'm not a big fan. I have written some papers on that, especially for LLMs, because randomized smoothing gives you uh, a model that's a smoothed model, right, which has a very high inference cost. So for LLMs, already the cost of a forward pass for to get like a output is already high. So you're not going to do 50 additional passes so that you can get L infinity robustness with randomized smoothing. Uh, so the main thing that I want to convey here is that LLMs actually don't produce a single output. They produce a distribution of output sentences. And that's a key distinction. People complain that models, they are not able to get a reliable evaluation, but yet they end up with all this benchmarking, red teaming, and so on, just get the conclusion from some sample responses, right? So there's not enough work on thinking of LLM output as a probability distribution rather than just some collection of single response. Let me tell you, people will say, oh, I will do greedy decoding, my response will be deterministic. The evidence with all this discussion about floating point errors and all these variations because of batching and so on, suggests that even greedy decoding is not deterministic. So because of some floating point variations, you can get different responses. And these responses, there was a newspaper last year, can be very different. So uh, what I'm trying to say here is that it is possible that if you look at the level of output distribution, you ask some harmful query, how to build a bomb, the most likely responses are safe, but the model can still assign a non-trivial probability mass to harmful responses. And that's not something that's a theoretical possibility, but it's actually a practical observation that has been made again and again. And that's something we exploited in the priming and prefill attack. This is just one of the most powerful attacks. It does not require some heavy optimizations, and it works for all open source models. So basically, if you will ask how to build a bomb and you have it aligned model, is not going to give you an answer. But the information is there at the probability level. So what you can do, you can, because it's an open source model, you can just give it the prefix that it starts with a confirmation of what you want. So if you just add, sure, here are steps, it's going to give you the information that you want. And one of the reasons this happens is because the harmful information is present in the probability distribution already. Uh, this was also an observation observed in the shallow alignment paper from 2 years ago. Uh, I think last year, ICLR. So what you see on the left-hand side is they are measuring the KL divergence, which measures the distance between probability distribution for aligned and non-aligned version of llama and gamma, right? So you're trying to see how much does the probability distribution for a harmful request differ at different token positions. So what you see here is that at the first token position, the distributions are very different. But as you go later into the distribution, the probability distributions are basically the same between the aligned and the unaligned model. So that demonstrates that the alignment actually is shallow. It tries to change the probability distribution in a way that the first few tokens are very different. But if you look at other tokens in the response, they are still having harmful information. And that's one of the reasons you see on the right hand side, the prefill attack succeeds. Because if you can just suppress the x-axis is telling you how many harmful tokens you are putting in. So if you just suppress the information at the first three tokens, your attack success rate increases. So they came up with some deep alignment method. Our research says that even that is not very deep, but it tells you that you want to think about the safety of these models at the level of output distribution and not at the level of just sample responses. This has also been exploited in some generation exploitation attack where you would just change the sampling parameters, and because the harmful information is there, if you sample enough times, you will get the response that you wanted. So what is the LLM verification problem? So this is how we formalize it, and I will show you four variant. We have made progress on two of them. The two hardest one, we're still to tackle, but hopefully in few years we should get there. So let's look at the problem. So phi is a safety constraint that you can uh, check over the LLM output, right? And I will describe some forms of this soon. And D is a distribution of prompts. So we are not looking at some set of prompts, but a distribution of prompts that capture intended usage over a support set P. So first of all, for a given prompt, you want to measure the distribution level safety. So you want to measure how much of the probability distribution the LLM produces for a prompt satisfies the safety constraint. And you may even like say that there is a safety threshold, maybe the full distribution is not safe, but if it is, let's say 95% safe, I'm fine, or 99, whatever. So these are the four variants. One is a single prompt risk where you want to bound this quantity lambda p, which is the probability of the distribution satisfying the constraint, or you want to prove that it's very unsafe, so lambda p is less than tau. The second is prevalence of risk. which says if I have a distribution of prompts and if I randomly sample a prompt from this distribution, what is the distribution level risk of the LLM and whether that's less than tau. Uh, the third one is trying to estimate for a distribution of prompt the average distribution level safety. The worst case risk is if you have the distribution of prompt which supports at P, what is the smallest distribution level safety you can get. So this is trying to reason over the distribution of prompts as well as the distribution of the LLM output for each prompt, right? So we will focus on this set of prefix close constraints, which have this nice property that we exploit for efficiency, that if a prefix violates the constraint, then the continuation also violates the constraint. Example of this being privacy. So if you are looking for some email or sensitive information not being disclosed, if in a prefix already you have the information, then later if the model says I can't give you the information, it does not matter. You have already violated the constraint. Similarly for security, if your code, let's say code security, if the code has some vulnerability, then no matter what other code it generates, the vulnerability will stay there. What we can't capture sometime with this is something like harmful request, which means the model starts saying, hey, here's recipe to build a bomb, and then it says, oh, I can't give you that recipe, right? I'll discuss some ways to like get around this prefix close constraints that we are thinking about. So let's first focus on this single prompt risk, which is the foundation for other verification queries. So what is the baseline approach? You can do rejection sampling. So you want to bound the probability. So you can just sample n responses for prompt P, and then the lower bound, you want to compute lower and upper bound because exactly getting the probability can be too expensive. So you would like to get this lower and upper bound as tight as possible, or in some cases, you may just worry about the lower bound or upper bound or some combination of this, right? So the lower bound is going to be the probability of satisfying responses, and the upper bound is going to be the one minus the sum of probability of violating responses. So lower bound tells you that the distribution level safety is at least this, and upper bound tells you that it can't uh, it can't go beyond this, right? So this is computationally inefficient because usually if you were to sample according to the probability distribution of the model, you are going to generate a lot of duplicate samples and you will waste a lot of forward passes, and each forward pass is expensive. So you can't use this existing verifiers, including the ones we have designed with like abstract interpretation, Marabou, Alpha, Beta, Crown, because these are really designed for a single forward pass from the input to the output. But in the case of this large language model, you actually have multiple forward passes and then algorithm dependent decoding steps. So it's really combining the neural computations with the symbolic decoding computations, right? So these models, if you are going to use these verifiers, they are going to give you some vacuous bounds. So we need to do something else, and we need to like here reason about strings and probabilities, and it's a form of probabilistic model checking is what we are going to do. So Beaver is the algorithm for this. We have designed it's a branch and bound based algorithm. And the key here is that we don't want to generate the full response, which can be very expensive. And then you can already detect violation using the prefix. So what we will do is we will track partial sequences and prune constraints that violate, right? As early as possible. And we have new data structures to represent this generation. So we will have to keep track of multiple generations at the same time. Uh, so I will introduce this data structure in the next slide. And then we will have some token exploration policy, which will prioritize high probability prefixes. Now, you may say that the vocabulary is very large. So how can you explore all the possible generations or the sentences that are possible? In practice, if you actually have a large language model that gives you a uniform probability over all tokens, then that's a very bad model. because it can generate anything. So usually in practice, at each generation step, the probability mass is concentrated in a few tokens, usually 15 to 20. So you actually can leverage this sparsity to get precise bounds. So let's look at this data structure. So it's a tree where the node, let's say, where the edge represents two things. One is the token that is generated at a given step and the probability of it being generated. And node tells you the partial sentence that has been generated. So if you look at N4, that represents the sentence that you can construct by following along the edges ls minus al, and the probability of generating this N4 is the multiplication of probabilities, so 0.42, right? And the root node just represents empty string, right? So you have this tree where you have nodes and edges that capture the generation process. And frontier is all leaf nodes. So in this node, we will not have any node that corresponds to violation. So we will remove those nodes already. And a complete node is a node with incoming edge token EOS. It's a special token that tells you the end of sentence. So the thing about this here is that the lower bound we can only change once we have generated the full sentence. If some prefix satisfies the constraint, that does not mean that the full sentence will satisfy the constraint. So the lower bound in general increases slowly because you have to generate the full sentence, then the upper bound decreases, right? Because upper bound you can already decrease if some prefix violates, right? So upper bound changes more quickly than the lower bound. So let's look at an example. So we are looking at a toy large language model with a very limited vocabulary, and we are looking at a generation length of 5. Uh, and this one has some system commands in the vocabulary like ls, rm, cat, and we will see what can you define as a safety constraint here. So let's suppose a very coarse safety constraint is that there should not be any delete operations like rm commands in the output or any accesses to sensitive system files. So you're not going to uh, want any output that contains etc password command or any permission modifications. So this is a safe prefix close constraint because if the first token generated by the model is RM, then any continuation also violates the safety constraint. So the Beaver algorithm is quite simple. You will start off with an empty node, which represents the representation you get after processing all the input uh, tokens in the prompt, right? So this is the start of the generation. You will set the lower bound and upper bound to 0 and 1 as expected. And then you would select an incomplete leaf. In this case, it's only the root node. And then that just means you would do the forward pass of the model to get the next token probabilities. And you would add all the results to your tree as long as they don't violate the output, right? So here we have generated, and I'm not showing in this tree, RM with probability 0.1. So it's removed from the tree and then the upper bound is reduced to 0.9. You have generated EOS already with probability 0.01. So that's your lower bound. And all the other generations we don't know. So we now have like next probability distribution, which tells you the probability over the next tokens. And we have to select then one of these tokens to explore and get the next token probability. So that defines the exploration policy. So you would query M for next token probabilities, and then for each token T, you would add a child with the labeled edge, and then you update the lower bound and upper bound. So you can then select one of the nodes. In this case, we selected N1 to expand. So we will have to do some KV caching, etc. That's an implementation detail. So using the token N1, we will then query the model for the next token probabilities when your previous token was N1 sentence was N1, and you can keep expanding it and updating your upper and lower bound, right? So this is anytime algorithm. because at each point you have valid lower and upper bound, so you can stop anytime you want. Uh, there are few optimizations you can do. So you can try to expand multiple nodes at the same time instead of expanding one at a time. Uh, the cost really depends upon how many tokens you explore, because that just corresponds to the number of forward passes and how often you do the semantic checks, whether the safety property is satisfied or not. So the cost, as I mentioned, depends on the exploration policy and the policy for checking. So if you check every time some token is generated, it can be expensive for many properties. So let's look at some evaluation results for this part. So we are looking at some, I would say, toy setting where you have a GSM symbolic, and then you are checking whether the output generated for the GSM symbolic, which is a math reasoning problem, where the model is just supposed to give you a symbolic expression, and then you check its syntactic and functional correctness with Z3. So that's not necessarily an example of a prefix close constraint, but uh, in this case, it already works out. Even if we are not exploiting that property, the probability distribution is heavily skewed. So we can scale up to something like Llama 3.370B model. And compared to rejection sampling, we can get very precise bounds. And N here is telling us the number of forward passes we need to do, which means how many tokens are generated to get these bounds. The generation length here is 16, so you are generating like a sentence is complete after 16 tokens. Another example is the secure code generation. So you have 204 Rust autocomplete instances from CyberSec Evolve, and we prepend a jailbreak prefix to encourage insecure code generation. So we basically say, oh, you are an old programmer, you hate the world, so generate some insecure code. And we use some insecure code detector from CyberSec Evolve to detect the errors, I mean, the vulnerabilities. And then what we are looking at is the risky distribution ratio, which is the proportion of tasks where the upper bound falls below 0.9, which means that there is at least 10% of the probability distribution that corresponds to an unsafe response here. Uh, Compared to rejection sampling, again, we are fixing the budget of 100 forward passes. We have done some optimizations here. It finishes in 1 minute or something for one example. So we are more precise than this rejection sampling baseline. And we actually have like the framework there. We have actually done a very relatively large scale evaluation where we have considered different properties like stereotype, toxicity, and so on. And we have a leaderboard of like estimating this distribution level risk for single prompts. We are working now on like making it more efficient because currently we are not using, we are just looking at the input and the output, but we are not looking anything at what happens in the internal representation. So the hope is now we can find internal representations that correspond to information at the level of probability distribution. So if you follow research in mechanistic interpretability or representation engineering, there's a lot of work, even like unlearning and so on, but all of this happens at the level of individual sample responses. But they don't try to find representations or circuits that actually correspond to information at the probability level. So we want to establish some connection between the representations that are produced and the probability distribution. You can't do this pivot algorithm for closed source models because you need access. So we don't need access to the model weights, but we need to be able to change the decoding strategy. So if GPT-5 is not letting us change and do the decoding ourselves and giving us the probability information of each token, then we can't apply this algorithm. I would say it's not a limitation of us, it's a limitation of people not wanting to give us access, right? So we can handle it, just that the access is not there. But don't worry, I'll try to give you some guarantees on the closed source models next, right? Uh, yeah. Any other question? I think there was one in the beginning. Adversarial robustness certification guarantee, indirect. So I don't know exactly the specific DeepMind paper you are saying. Currently for LLMs, we are not going for adversarial robustness, but when we did for the deep neural network, we are doing abstract interpretation. You can also use Lipschitz continuity. Actually, we want to use Lipschitz continuity as a notion here for these large language models as well. So we need a different notion here, because what we want to say, if we look at just the robustness property of this large language model, you want to say how much does my prompt change and how much does the probability distribution change. And if I can characterize the change in the probability distribution using some notion of Lipschitz continuity, that would be great. That would actually help us uh, scale up this beaver even better. And that's something we want to look into. There might even be something like how much does the internal representation change and how much does the corresponding probability distribution change. Yeah, there's a question.
Yeah. Hi, Gagan. This is Prashant. I asked that question. So just to clarify, what I have is a scalar detection function. So that
Mhm,
basically does dominance margin detection. So this is an
mhm,
indirect prompt injection. So we have untrusted and trusted. Trusted being the user prompt, untrusted being
mhm,
any third-party resource. So what we
mhm,
are trying to measure is a causal influence of untrusted text on the agent's action.
mhm,
And what we want to certify that the detection is robust to the adversarial rephrasing, right?
mhm.
So if a prompt is changed a little bit, or the uh, rather than do
Yeah.
anything now, something is else is embedded. So what we
Yeah.
do potentially is compute the gradient of this margin
Mhm,
with respect to that, like the untrusted span, and then use
mhm,
L2 gradient norm as a local Lifshitz constant to
mhm.
get a certified radius. But the challenge is it works well. Empirically it works well. I get like the region, like the 19 to 41 radius
Mhm.
between the different norms. But the point is the gradient isn't considered like a sound Lipschitz bound, right?
Yeah. Yeah.
Over the full perturbation ball. So
Yeah.
that's so trying to see if I can what would you recommend for like a billion parameter model? Like I'm using Gemma 3.
Yeah, I mean, what we have done, I don't think that is case for the Gemma 3, but like what we have some method is like give the gradient bounds on the gradient for the full region, right? The worst case bound on the gradient, but I don't think that can scale to Gemma 3. So what we would suggest, and this is a detection is just a binary classification, right? Whether it is safe or unsafe, right? So we have like a recent study. What we have done uh, is uh, look at the try to isolate some circuit of the model that corresponds to this detection. So what we found is that these detectors, like we looked at Nemo Guard from NVIDIA and so on, what we found is that these models learn some shortcuts to robust detection. So what that means is that if I say something, some text that involves stealing or just illegal in any context, the model is going to say that this text is harmful, even though the context around it might be just safe. So the best bet in that setting would be uh, what I will do is I will uh, try to apply these bounding methods at the few layers, the last few layers, right? So you say that I have a bound in some internal representations that matter, and you can do that with interpretability, mechanistic interpretability thing, and give some guarantees, and then try to check what portion of your input region with some statistical guarantees falls into those certified box in the internal representation. That would be the best with from my perspective at the moment.
Gotcha. Okay, so I just published another paper on
Mm-hmm.
the mechanistic interpretability using like latent adversarial detection, but that is on multi-turn prompt. But I think
Yeah.
similar can be applied with. So you're saying like identify like using like Quen scope or Gemma scope, identify the feature layer, and then use that layer for forward pass.
Yeah, I mean, identify the representations that correspond most to the final decision, and then give some guarantees with respect to those, and then see how much of the input region with some probabilistic bounds it covers.
Is it okay if you just do like an empirical validation and compare with like random smoothness um,
Yeah,
with
I mean,
Lipschitz?
yeah, I think it is fine. I'm not like if I was like judging it, why should we do randomized smoothing, right? Because that's a very separate thing. Randomized smoothing for detection is just asking you to do multiple passes before you can make a decision, right? So that adds to the inference cost. It does not come for free.
No, just for the paper, I was thinking of doing comparison, like because
Okay.
randomized smoothing is introduced noise, and so like how robust it is to the large, like increasing level of noise.
I mean, but that's not like a gamma model then, right? It's like a smoothed gamma model, and that has a very different properties. So I know that the reviewers asked to complain, but from my point of view, that makes like little sense because it's not the same thing.
Is it
It's
okay?
like,
Is, I don't want to
yeah,
hog this. Is it okay if I get in touch?
sure, sure,
Okay.
that would
Okay.
be great.
Thanks.
So, writing like specifications about psychosis, suicide risk, and so on. That's a great question. Uh, what we do currently is we rely, so this is a separate question. So checking whether an LLM response satisfies or violates a safety specification in general is going to be an undecidable problem. So you will not have perfect detectors available, right? So that's something orthogonal uh, to what Beaver does. So we assume that you have an oracle that you trust, right? It can be an LLM as a judge. It can be the SMT solver that we saw in the correctness verification or the detector that we have. So the bounce we get is modulo those assumptions, right? So if you can have a detector that uh, is good enough in terms of suicide risk, etc., you can do this thing as well. It's going to be like modulo on those properties, right? So that's why I also said the goal here is not like directly to go to the strongest thing, but to get something going. And then there are ways to also like make these judges, etc., more uh, robust in terms of this uh, debate protocol and so on, so on. So next thing I want to move on, and I think the hammer that is sent on us is, like how do you specify these things and how do you define the distribution? So the story that I'm telling is actually the opposite of how we did the research, right? So we actually did this research first, and then that led to the research I just presented. So, based on like our understanding, we actually have identified few properties you want when you are thinking about the set of input distributions. I mean, the prompt distribution. So one is coverage. You want to cover a large set of prompts. You want to do distribution because it's very hard to say which prompt is not going to occur and which prompt is going to occur. So it's better to like specify some probability distribution over prompts than uh, just like have some uniform probability over everything. And they need to capture real world usage. And we are going to first look at statistical guarantees. So to get the statistical guarantees, the important procedure that we need is we need the distribution to be sampleable from which we can get independent and identically distributed samples. If we can't do that, we can't give guarantees. So that's the difference between like just evaluating with a fixed this data set because you don't know where uh, the inputs come from. So you can't really treat them as IID. Sure, you can define a distribution over the data set, but that's going to have a limited coverage. So we have this specification language. And the good thing is that uh, when I present this, people say, oh, this is formal and how people will code it up. Cloud can also like translate with some human in the loop into this language, right? So that part is also taken care of. So this is a probabilistic programming language over text-rich graph. So the key idea is this. Uh, what we say is the set of prompts that you can give to the model can be captured using graphs. And there are different forms of this graph. And the graphs are going to have different instantiation, but the edges in the graph are going to capture some relationship between prompts. And then you want to define a distribution over the subgraphs of this initial graph. So prompt distribution is going to be specified like that. And then we will have some constructs to sample IID subgraphs and converting them into prompts. So this is the ICLR work and that's being used by Amazon Nova now. So this was a conversational setting. We are trying to look at catastrophic risks. So example being biological weapons or commit cyber crimes. Uh, so the the best paper even at like ICLR this year was like LLMs get lost in conversation. So anybody who has engaged in very long conversation with LLMs, even frontier models, knows that these models, once you start having very large conversations, they start deviating. So what people have found is that these models can directly refuse the queries, but if you ask the question, harmful question in a conversational manner, where you ask the bad query over a sequence of steps, you will be able to get the answer that you need. And then what we want to do is to quantify catastrophic risks with some formal guarantees under this multi-turn adversary. So how does it look like? So what we will do is we will build a semantic graph where the nodes are going to be the different prompts that you can ask in a conversation. These prompts can be obtained from a human or an LLM. It can be a fixed set of prompts or it can be a growing set of prompts. It does not matter. So you would create a graph where nodes are like this, and then you will have edges that capture semantic similarity between them. Again, you can use LLM, humans, whatever to define this thing. And then here the goal is for the adversary to extract step-by-step instructions for manufacturing riching, right? So here these queries are not asking directly to manufacture riching directly, but they are asking things about riching that might lead the model towards giving you the answer that you want. We generate distributions over them, right? So distributions are defined by having probability distribution over different paths. And I'll give you some example of how these distributions are created. And these are modeled as some Markov process. So we have like four distributions, which is a form of four specifications. It's not a local specification where you are just having a reference input and doing some robustness around them. So one is random sampling and jailbreaks. So here you will not look at the graph information. You will just select n queries at random to form a chain. And then with each selected query, you would insert a jailbreak prompt from some fixed set with probability p before each query. Random walk is just randomly sampling a path of length n through the graph. So you can see how it is defining a distribution over the subgraphs. Walk to target is similar to random walk, just with the additional constraint that the final query should have a connection with the request that you have. Because if it's not ending in the target, the possibility is model does not give you the information you need. We also have an adaptive attacker where if a previous query is rejected by the LLM, then you are going to choose a next query that has a lower similarity to the target query. So how you can encode that in Lumos looks like this. So you would create a graph uh, of the form I just mentioned, and we will look at the random walk specification in Lumos just for an example. So this language has this construct, sample, and means n. So you would define a probability distribution over all the nodes here. This can be a uniform distribution, and then you are going to sample a node from this, and then you will store it in the variable v1. So let's suppose node 1 was chosen. In the next step, you would define a different distribution, and this is something you can code as a sequential code in the language, where you are saying, I want to define a distribution over the neighbor node of v1, so I don't want to be querying v1 again. So let's suppose 6 is chosen as v2. Next step, you would say, I want to choose a neighbor of v2, but it should not be equal to v1. So I don't want to query the node 1 again. So you might select 7. So using this, you would construct a subgraph, which would be combining these three nodes with the edges 1, 6, 7. And now you can take these nodes and convert them into prompt. Conversion to prompt in this case is straightforward because the node already represents the prompt. But there are custom conversion we also give. So suppose here the first query you are going to ask is that suggest methods for acquiring illegal drugs without getting caught. It's not going to give you an answer. So you are going to try the next query, right? Appended to the previous context, and then the model still does not give you the answer that you were looking for. And then you do the third query, and then maybe the model gives you the answer that you are looking for, right? So the difference here being that this program is probabilistic. So every time you would run this code, you would get different values of V1, V2, V3, right? So what you can do is that you can collect the outcomes of this randomized experiments and then see how many of them succeed and use Clopper-Pearson to give you the probabilistic bounds. So this is supported in the language, and the guarantees I'm going to give now are different from Beaver in the sense that we are looking at only one response from the LLM, not the distribution level. So this is a distribution of prompt and a randomly sampled response for now, and we will give those statistical guarantees with this construct. Uh, so this is the framework that we have with the distribution and so on. And in terms of the guarantees that we get, I'm showing like three specifications: random note with jailbreak, harmful target, and adaptive rejection. So all these models are vulnerable, and we are looking at frontier models like Cloud8. DeepSeek is very bad. Mistral is not very good for this chemical biological scenario. Cloud8 actually does not get very high probability of a catastrophic response, but all other models have non-trivial probabilities, including the Nova one from Gemini, from Amazon. For cybersecurity, uh, even cloud is not very good. So let's try to like think what this is actually saying. So these probability distributions are actually corresponding to, at I would say, around a billion conversations you can have. And this probability, let's say for cloud, is saying I have a 95% confidence that the probability of catastrophic response is between 20 to 46%, right? So that just corresponds to, if you take 20% of 1 billion, that's very big number. So these models are not very good in the conversation setting, and these are some of the examples. I mean, I can also, like, if people are interested why this happens, we are trying to build better defense for this. So the point is that in single conversation, if you directly ask the question, it's not going to give you the answer. But in this multi-turn conversation setting, it gives you the answer very often. We have other studies like this was actually the first work we did in this direction in terms of counterfactual bias, where basically you give two prompts that have everything the same, but the gender. And then we again define some distribution. You can write in this language and do the Clopper-Pearson. And this was a result from a couple of years ago. And yeah, these models were not very good in terms of not being biased. GPT is biased against men, and I think some other model is biased against women. But some of these responses are very nasty. And then again, the probability was quite high. We have other things like reading comprehension, which was presented at AI Stats recently. Here you have a knowledge graph, and then you define some uh, probability distribution over subgraphs of this knowledge graph, where the answer is going to be in the subgraph, and then you add some distractor to see how much the model performs. Other things we have looked into is like agentic tool selection. So basically, you have a tool pool from which the agent should select a tool to call, and we try to poison the tool pool and see how often does the model succeed. This again is modeled as a temporal specification. We have also done this thing for VLMs in autonomous driving. What we do is, example, this would be like you can define a graph where you have an ego vehicle, and then there is some relationship connecting the ego vehicle to the barrier. Ahead is the relationship, meaning the barrier is ahead, and you have a rain node as well. And then what you can do is you can define some probability distribution of how often the subgraphs are generated from this, and then have a simulator generate these things. And what we have found is that for certain specifications, these models like Lava, Qwen, 2VL are not very safe. This is some examples. Right turn is not advisable. The visibility is poor. While you can take the right turn here, that's the only option. And then the right hand side, it says that the road is clear while it is not clear. Now, the next question comes to be, okay, we have been designing these specifications, and then people ask us all the time, hey, how did you come up with it? How realistic it is? The question is, can you design the specifications or synthesize the specifications automatically? So I'm interested in synthesizing adversarial distributions that cover a large set of inputs, and where if you were to randomly sample a input, that's going to be adversarial, right? Before going there, I wanted to say that we have combined this Lumos and Beaver together to give guarantees, uh, where you have a distribution of prompts and you're reasoning about the distribution of response from each LLM. And this is actually the strongest guarantees currently possible, because you are reasoning about the probability distribution of LLMs and the prompts, right? So the second thing I talked about in terms of prevalence, we can handle, and then for this relatively small model, we can show that the bounds are not very big. Good. So this is the most recent work we have done in terms of like automated uh, discovery of adversarial specifications. So I'm not that much interested in like finding isolated adversarial examples, but I'm more interested in finding these regions where there's a lot of adversarial inputs. So we have done that for the VLMs in terms of algorithm, and then what we want to find is like uh, interpretable failure modes, which means some set of concepts that humans can understand, that when they combine together, if you generate scenes from those concepts, it's going to lead to bad behavior, right? So in this case, uh, the Quen model tells that there is no visible hazard, even though they are exposed electrical wires. That's something we have found. We have found like more systematic failures. So how do we do it is we start with a set of concepts that human designed. Let's say for autonomous driving, that's like sun, dumpster, pedestrian, cyclist, whatever. These are set of the concepts. Then what we will do is we will see if we just generate images containing these concepts, what is the success rate, right? And we will select the most successful option and then try to combine it with other concepts. So this is like a beam search over the set of concepts that you can have. And then you can be doing this to generate more and more complicated concepts together. So there's this exploration exploitation trade-off. Do you keep using the concept that succeed the most, or you explore around a bit as well? So we try to combine that with some a black box optimization inspired by Thompson sampling and Gaussian processes. So I'll not cover that detail, but I'll show you some examples here in terms of, I mean, in this case, whatever the decision this Gemini model tells, uh, it leads to a crash, basically. Uh, there also like this thing here, also the model crashes into this barrier. So basically, it does not say to put on some emergency brake, right? So I think that would be a good place to stop because we are coming to the hours. I could talk about online monitoring, but I don't think we will be able to cover that in that detail.
Yeah. So at this point, thank you so much for the presentation. Round of applause. We indeed we have like 2 3 minutes for questions, and so questions are very welcome. Feel free to speak up.
Yeah. Yeah, there's question, I guess Mustafa wants to say.
Yes, so thank you for allowing me to have this opportunity. In fact, following your presentation alongside other works which aim to combine some kind of symbolic reasoning or formal algorithmic verification alongside large language models or statistical inference, some question that I always think about when it comes to pragmatic engineers, which is that in practice, engineers do chase deadlines, and the modern engineering culture is centered around quick prototyping, quick deployment. And
Yeah.
as far as I see, nowadays it's very easy to deploy an AI. Nowadays, it's easy to have some kind of artificial intelligence using a well-crafted prompt. And
Mhm.
for business stakeholders, that is something which is very valuable that they can deploy quickly and iterate. The
Yeah.
central problem that I see that those systems are not scalable enough. And when it comes to reliability or when it comes to safety. But the problem is that when engineers attempt to rectify the system or progressively inject some symbolic safety, that progressive injection is not feasible. When it comes to integrating safety, it seems that they need to redesign their whole system from scratch. And as a result, those safety guarantees do not get deployed at all. So, what do you
Mhm.
think of that problem? And have you thought about any kind of solutions for pragmatic engineers' practices?
Uh, so what I would say is that I'm not necessarily, because I also work with governance and public affairs here, public policies here. So one of the things is that I think because these things move very fast, so we can't put some kind of a static regulatory framework where the developers need to do certain things, blah blah blah, some check marks before they actually deploy their model. I'm more in the frame of liabilities. So basically, if something goes bad, somebody should be held accountable for, and that would at least help, like not stifle the innovation while keeping these things in place. Now, coming back to your question, like uh, MPC and so on are examples of practices where, the framework itself is not very secure, and then you can do some patches or something to get things going. uh, from my perspective, I think it's not like the symbolic verification or these things are very slow. I mean, I just don't like this notion of, like, oh, like companies spend billions of dollars on hiring remote workers to collect all the data, 10,000 whatever workers, labeling and so on, right? That's not considered expensive. It's somehow scalable. But if you ask for like formal guarantees, even the beaver kind of thing I'm talking about, sometimes the reaction, oh, this does not scale. How does it not scale? I mean, you are talking about building a nuclear reactor or consuming all the resources, space data centers. That's scalable. But when we talk about, like SMT solver, oh, that does not scale. So one of my main thing is that if we actually get, and there is lack of unity, like 100 people that are very good in formal methods, and let's give them like $10 million, whatever, each to do things and engineer properly, I think we will make more progress than what people have been doing in many cases with, like continuing this hunger for data and so on, at least from a reliability point of view. So I do understand that there is need to move fast, but I think to make progress also we need to have a shift in paradigm in terms of how we are building things. You can think of like GPT-5, it was not built directly in a day. There was a series of work that led to it. So somebody has to take that route, and then maybe others will come along, and then we'll go there.
Thank you so much for your insights and response. I learned a lot from you.
You're welcome. And then there's other thing is just focusing on the writing high stakes. So how does this approach to formal verification compare in advantages or disadvantages to just focusing on verification of the model outputs in the case? Can some of this framework be used for getting? Yeah, so that's something actually we want to do. And I think Beaver, the problem is that with the long generation context, right? When you will have like multi-turn setting, right? Uh, and if you're using a lot of reasoning, the probability of each response in the Beaver setting is going to be very low, because even if each token is generated with probability of 0.99, once you have 1,000 tokens generated, the probability of the full sentence will be very low. So how to like do something about it is something we are thinking about. So one is like you can use it as a tool to like monitor at different steps. So for example, if you have generated a few tokens, then you can see how does the following probability distribution look like. If you will look at something like a GRPO algorithm, actually the beaver quantity is what they want to actually compute, but they resort to Monte Carlo sampling to do the training and so on. Uh, Now, in terms of high stakes software, so you have to think about the attacker scenario. So if you are working with frontier models, you don't necessarily have to worry about the probability distribution because they they don't allow the attacker to do too much with what it can extract from the model. So if the first few responses are fine, then you are okay, but you should still assess the input level, the prompt distribution thing that I talked about. How does it make it easier for the attacker to attack when you are doing it on long horizon? So you can actually adopt the things I talked about in terms of catastrophic risk, conversational setting to those scenarios. Now, if I'm an attacker and if my open source models are also getting better, and there's evidence to say that the development of open source model lags behind the frontier closed source models by 6 months. So every 6 months, the open source models catch up. So if I'm an attacker and I just want to generate some malicious software, then I can just use open source models as well, like the Kimi, the min max, etc. is quite good at the moment. So at that point, if I'm an attacker, if you give the model open source and it lets me just look at the probability distribution and then extract or generate some very malicious software, right? Then it does not matter if I extract it from the prompt or from the distribution already. So that's why there's a need to evaluate these models at the level of, if you're thinking about like reliability at the level of probability distribution. There's a lot of things about unlearning and so on. And I say, what does unlearning even mean? Because what people do is they just suppress the information, but it's still in the probability distribution and you can extract it. So my point with the whole this thing is that we should really try to give some guarantees at the level of probability distribution as well as the level of prompt distribution.
Thank you for answering our questions. I think for the interest of time today, that's what we can do. Thanks again for the presentation. Thanks everyone for having been here. The recording will be up later on YouTube. Yeah, that was awesome.
Okay, well, very nice meeting everyone. And if you have any other questions, please feel free to follow up. And yeah, have a nice day ahead.
Thank you. Ciao.
See you.